Hi, my name is Youngmoon Lee from Hanyang University, Korea. Today I will present our paper, Causes and Fixes of Unexpected Phone Shutoffs. This is joint effort with University of Colorado Denver, University of Michigan Ann Arbor. Many users report their phones shut off unexpectedly in cold weather even if they have plenty of battery capacity remaining. This unexpected phone shutoff is a real problem for many users, and numerous news articles cover this. These unexpected phone shutoff problems are prevalent in cold environments, especially in old phones. Phones suddenly shut off even at 40% of remaining battery capacity or SOC state of charge. Our survey reveals almost 80% of users are concerned about such unexpected phone shutoffs, and 60% of users actually have experienced this. Also, 66% of users expect to use their phones beyond the battery warranty period, and 85% of users are concerned about battery degradation and associated shutoff problems. Consequently, unexpected phone shutoff make users cannot make important calls messages reliably. Furthermore, users cannot fully utilize their phone battery capacities. The right figure shows the phone operates about 2 hours in cold temperature and unexpectedly shut off at 23% capacity. Then the phone is warmed up and it can turn back on. The phone could operate 1.5 more hours and 19% of remaining capacity can be further utilized. We first need to understand phone and battery dynamics to understand the causes of phone shutoffs. The figure shows the battery model on the left side and phone on the right side. Phone requires cutoff voltage level from the battery, otherwise it will shut off. Battery is modeled by voltage source called open circuit voltage and battery resistance. Discharge current flows through battery resistance and causes a voltage drop across the resistance. In cold weather, battery resistance increases. If peak discharge current is applied at the same time, the voltage drop increases dramatically. As a result, battery voltage may fall below the cutoff voltage level and the phone goes offline. Such voltage drop increases with the battery resistance. Battery resistance significantly increases in cold temperature. The left figure shows the measured battery resistance under a wide range of ambient temperature. Beside the temperature, resistance also rises with low SOC levels. These demonstrates battery resistance non-linearly changes with both temperature and SOC during phone operations. This battery resistance also rises over battery aging and degradation over longer period of phone operation. Left figure shows battery resistance increases from 100 to 200 discharging cycles. Finally, battery resistance may significantly different depending on the usage pattern and the degree of degradation. Right figure shows the battery resistance is very different for two phones, same model, at the same discharging cycle. This phone-specific nature of battery resistance make it difficult to address the unexpected phone shutoff problems. On the other hand side, discharge current is dynamically changing with user workload. Left figure shows the resistance and discharge current traces. The phone is loaded at around 3600 seconds with a large amount of peak current. When we plot the voltage drop versus current times resistance from the trace, the voltage drop significantly rises with the increase of current and resistance product. We now know both battery resistance and peak discharge current dynamically change. This dual dynamics of battery and system make the battery voltage drop beyond the cutoff voltage level. This causes the unexpected phone shutoff when uncontrolled peak discharge current is applied at increased battery resistance. After examining the causes, our goal is to mitigate unexpected phone shutoff. We aim to solve the problem on commodity smartphones without any special hardware or software components. The battery resistance is different even for the same phone model. That's why we first need to accurately capture the phone-specific battery profile. This must be done on device. We also need to leverage the existing system software, the battery and power management system on commodity phones. To solve this problem, we developed BPM, Battery Aware Power Management. BPM divides the problem into three sub-problems. First, how can a phone capture its battery resistances without additional hardware? In short answer, BPM generates charging pulse on the phone to accurately estimate battery resistance and build the battery model. Second, after capturing the battery resistance, how BPM controls discharge current to maintain battery voltage level. BPM monitors the runtime discharge current and using the discharge model, limit the maximum CPU frequency. Finally, how to deal with peak discharge current caused by bursty user workloads. BPM schedules resting period in OS level during the peak workload to recover the battery voltage level. To capture accurate battery resistance on device, BPM leverages charging time to characterize battery resistance. Specifically, BPM generates charging pulse by enabling and disabling charging. To prevent the overcharging, modern battery management system allows softwarely disabling charging. BPM uses this feature to alternate charging and non-charging to generate step input of charging pulses. From the step response of battery voltage, BPM estimates battery resistances that help us to predict the voltage drop. This pulse charging is only done overnight. This is because first, the minimal user interaction enables accurate resistance estimation. Second, overnight charging allows enough time for this pulse discharging process. Our survey indicates 75% of users are willing to profile battery overnight. Also, this pulse charging helps mitigate battery degradation by resting battery, according to our MobiSys 17 iCharge paper. Finally, estimated battery resistance is recorded with corresponding SoC and temperature to construct the battery model. BPM incrementally updates battery resistance at different temperature and SoC on the lookup table. Then using estimated battery resistance, how BPM controls discharge current. During discharging, BPM monitors discharge current and regulates it below the maximum allowed discharge current, not to drop the voltage level beyond the cutoff level. BPM reduces discharge current by enforcing the maximum CPU frequency based on the discharge model. Basically, BPM feedback controls the average discharge current every control period. BPM also schedules resting period in between task executions. During peak user workload, the continuous discharging may drop the voltage level beyond the cutoff level. BPM schedules the right amount of idle periods to recover the battery voltage to safe level in between discharging. While CPU frequency control helps BPM to meet allowed average discharging current, this OS level control knob helps BPM to spread out peak discharge current close to the average level. These two tightly coupled mechanisms allow efficient battery-aware discharging. BPM tackles the unexpected phone shutoff problem with two novel charging-discharging schemes on the commodity phones. BPM first generates charging pulses to acquire accurate battery resistance from the voltage responses. The battery profile is done overnight to establish comprehensive battery model. This provides real-time battery profile for discharging phase. During discharging, BPM limits the maximum CPU frequency to control the average discharge current and maintain operable voltage level. Finally, BPM schedules resting periods to regulate peak discharge current near the average level to avoid peak voltage drop. BPM is implemented as a middleware on top of OS Linux kernel. Using the existing battery management driver, it controls the fuel gauge chip for burst charging. Inside BPM, battery profile is constructed during overnight charging and used during discharging. BPM also uses OS power management interfaces to set the maximum CPU frequency and schedule idling threads. BPM only limits the maximum CPU frequency, not directly controlling it, so it also collaborates with existing dynamic power management scheme. We now turn to the evaluation. We used commodity smartphones, a Pixel, two Nexus 5X, and a Nexus 6P from different OEMs, Google, LG, Huawei. They have been used for different discharging cycles, but all the phones are within battery warranty periods. We used popular mobile workloads including YouTube video streaming, 3D gaming, and UI Exerciser. UI Exerciser generates random touch input events. Since we measure battery performance, our methodology is to experiment full discharging cycle while running each app. We measure battery and system performance to compare with and without BPM. The figure shows the trace for full discharging cycle with and without BPM. Blue line corresponds without BPM and orange line corresponds to with BPM. On the top left figure shows the orange discharge current is effectively regulated compared to the blue. That's why even with the similar battery resistance, BPM can regulate voltage drop to the lower level shown on the top left. Finally, the battery voltage could be maintained a longer period of time. As a result, the phone can maintain cutoff voltage level, operate until near 0% SOC, and extract 38% more capacity out of the same battery. We then repeat the same experiment 10 times to analyze the trade-off made by BPM. The figure shows operation time versus discharge current and CPU frequency. Discharge current is reduced to regulate the voltage drop and operation time is extended. In this operation time versus discharge current trade-off, BPM shifts the trade-off to the top right position by effectively preventing the premature shutoffs. The product of XY value in this graph is the extracted capacity, and the BPM allows increased capacity extracted from the same battery. To achieve this, frequency is reduced by only 1.1% from 1.2 GHz to 1.18 GHz. Our survey also reveals 70% of users think preventing unexpected phone shutoffs is more important than the achieving maximum performance. We also analyzed the actual application performance from user point of view. We measured latency of UI event, FPS of YouTube streaming at room temperature and -5 Celsius. With BPM, median latency of UI task increases from 108 milliseconds to 119 milliseconds at room temperature, 77 milliseconds to 104 milliseconds at -5 Celsius. Latency increases by 11 to 27 milliseconds, but the phone operates longer period of time and processes 7 to 49% increased UI tasks. Likewise, in YouTube streaming, FPS is reduced by 2% to 6% only, but the phone can stream 23% to 71% longer period of time. Finally, we analyze the impact of BPM in different temperatures. The figure shows discharge current and operation time across different temperatures without BPM, blue, with BPM, yellow, from room temperature to freezing temperature, 0 degrees Celsius, without BPM, operation time reduced from 159 minutes to 135 minutes by 15.1%. With BPM, operation time is reduced from 163 minutes to 154 minutes by only 6%. The results demonstrate the impact of BPM pronounces at low temperature, and it can maintain much more reliable operation time across different temperature levels. Battery-aware power management, or BPM, is about bridging the gap between complex battery behaviors and system management. We found uncontrolled peak discharge current applied at increased battery resistance causes unexpected phone shutoffs. BPM demonstrates on-device battery profiling and battery-aware discharging on commodity smartphones without any additional components. We have implemented on a number of smartphones from different OEMs. Our evaluation shows BPM can extend device operation by up to 30%, mitigate operation time reduction from 50% to 6% at freezing temperature. Thanks for listening, and I'm happy to answer any questions.